Hi, hello, welcome to Shasha Education. Now we go to see about chemical bonding too. First of all, characteristic properties of ionic compounds. These exist as crystalline solids in which the ions were arranged in a regular three-dimensional structure. The ionic compounds are generally hard and brittle in nature. These compounds have high melting point and boiling point due to strong electrostatic interaction between the ions. These are generally soluble in water and less soluble in nonpolar solvents like ether, alcohol, etc. These conduct electricity when in matter molten state or in aqueous solution. Next, causal theory. It explains bonding quite well, but only for a small class of solids composed of electropositive elements of group 1 and 2 with high electronegative elements. Secondly, this theory is incapable of explaining the formation of molecules like SO2 or O2, etc. For example, in the case of O2, there is no reason to expect the one atom of oxygen would lose two electrons while the other accepts them. The problem was solved by Lewis' theory of covalent bonding. Covalent bonding, Lewis' theory. Lewis assumed that atoms attain noble gas electronic configuration in the process of bond formation. However, the way the noble gas electronic configuration is achieved is different. Lewis proposed that this achieved by sharing of a pair of electrons between the two atoms. For example, two hydrogen atoms chemical bonding form a molecule by a share of pair of electrons. If electrons are indicated as dots, formation of hydrogen molecule can be shown as HH2 coordinate covalent bond. In some cases, both the electrons of the shared pair are contributed by only one species, atoms, molecule, or ion. A common example is the formation of a bond between boron trifluoride and ammonia. This is coordinate covalent bond. The bond was represented by an arrow symbol. Next, bond polarity and dipole moment. A covalent bond is formed by sharing of a pair of electrons by the two atoms, each one of which contributes one electron. If the two atoms have the same electronegativity, then the sharing of the two bonded atoms is equal. Such a bond is pure covalent bond. It is nonpolar in nature. However, if the electronegativities of the two bonded atoms are different, as in HCl, then the shared pair of electrons lies more towards the more electronegative atom, that is chlorine. As a result, a small negative charge delta minus develops on chlorine atom and the equal positive charge delta plus develops on hydrogen atom. The covalent bond in HCl is a polar covalent bond. Next we see about dipole moment. Dipole moment mu is equal to magnitude of charge q into distance of separation r. It is commonly measured in the unit d by symbol d. The SI unit of dipole moment is coulomb meter cm, capital cm, small cm na centimeter, coulomb meter capital cm. The two units are related as 1d is equal to 3.336 into 10 power minus 30 coulomb meter. Dipole moment of same molecule dipole moment of some molecules, HF, electronegativity of halogen atom, 4, dipole moment is 1.90, HCl hydrochloric acid, electronegativity of halogen atom is 3, dipole moment is 1.04, HBr, electronegativity of halogen atom is 2.8 and the dipole moment is 0.79. HI, electronegativity of halogen atom is 2.5 and the dipole moment is 0.38. Dipole moment is a vector quantity since it has direction and magnitude both. By convention, the simple arrow 1 dash is used to represent dipole moment. For example, carbon dioxide CO2. CO2 molecule is a linear diatomic molecule. Each C double bond O bond is polar with the oxygen atom having the negative end of the dipole moment. The dipole moment of both the CO bonds have the same magnitude but are in opposite direction, hence they cancel each other. The net dipole moment of CO2 is 0. Next, ammonia NH3. NH3 has a pyramidal structure which makes the arrangement of 3 NH bonds unsymmetrically. In each NH bond, nitrogen is the negative sender and the hydrogen is the positive sender. Bond and orbital dipoles, first figure. Next, second figure, net bond dipole and orbital dipole moment. Next, third figure, net dipole moment of the molecule. Thank you. Do you want more videos? Please subscribe our channel, like this, comment this and share this. Thank you.